Theory of relativity is a combination of two different theories, or say two different combinations. First, one is Einstein's special relativity theory and second one is general relativity theory. Concepts included in theory of relativity consider space-time as a single unified entity. According to concepts of theory of relativity, following are the elements of unified entity of space-time. Space and time, of course, relativity of simultaneity, kinematic, dilation gravitational time, length contraction. Term of relative theory was firstly used by Max Planck in 1906. The whole theory of relativity is based on this term. Max Planck described how the principles of relativity theory could be applied on practical events and various theories. Later on, in the same discussion, term theory of relativity was used by Alfred Bucherer. Relativity theory is considered a unified representative of multiple physical theories. Concepts from more than one physical theory are explained and broadly discussed in this theory, which makes the theory real broad and deep. During 20th century, concepts and ideas of theory of relativity has transformed many theoretical concepts of physics and astronomy. In the most basic version of theory of relativity, 200-year-old theory of mechanics was used as a base for further studies and descriptions. Isaac Newton is said to be the founder of theory of mechanics, not the whole theory, but he developed and explained many concepts that are contained in theory of mechanics. The whole concept of gravity was introduced by him. In physics, theory of relativity contributed a lot to develop or improve the concept of elementary particles. Concepts of relativity theory were used to understand interaction of elementary particles more deeply. Theory of relativity also helped the world to move in the right direction to reach enhanced nuclear era. Not only physics have theory of relativity also contributed in fields of cosmology and astrophysics. Thanks to the application in theory of relativity, astronomical phenomena were predicted and eventually proved real too. These phenomena are consisting of following: neutron stars, black holes, gravitational waves. As described, theory of relativity not only helps researchers in physics, but also in cosmology and astrophysics. This broad theory became concerned for cosmology since the basic concepts as black holes are explained by theory of relativity. Many concepts that are a part of astrophysics use many concepts and ideas of theory of relativity as a base for further researches and explanations. Being a solid combination of multiple theories, theory of relativity becomes a thing of concern for practitioners of physics, astrology, cosmology and astrophysics as well. Main concepts of theory of relativity are covered. Both parts of this theory, which are general relativity and special relativity, are discussed broadly. This short introduction covers from history of this theory and to scope of the very same theory. It will provide a breakthrough in the broad theory of relativity that will help beginners to cover broad concepts easily. If one has a glance at historical events related to theory of relativity, he may find that many theoretical results that mean a lot for physics and cosmology are included in it. The concept of theory of relativity began to spring as Albert Einstein disclosed his researches about special relativity. Work by Max Planck and Hermann Minkowski contributed a lot to help this broad theory develop and improve. Albert Einstein holds a special place in this place since he is considered a father for both general relativity and special relativity as well. He introduced the concept of general relativity in around 1907. In the time span of 1907 to 1915, many other theorists and physicists contributed their work and developed this very same theory at its peak. Theory of relativity still requires experimental verification in some of its concepts. Some physicists consider theory of relativity just a theoretical concern that can be proven practically. Despite of this criticism, the result extracted by analyzing the relativity theory are excessively important for practical engineering. Practical engineering is concerned about theory of relativity in following concepts: GPS, global positioning system, GLONASS, Galileo, forthcoming one, concept of high precision dissemination of time. In these concepts, or while practical implementation of these ideas, if relativistic considerations are not considered, particle accelerators from electron microscopes will fail for instrumental ranging. According to Einstein, principal theories are the origin for the theory of relativity. He referred the concept as analytic methods. He managed to prove that concepts that are a part of theory of relativity do not use hypothesis as base, but they instead use empirical theory as a base for further discoveries and research for new concepts as well. Using the concepts of theory of relativity, various mathematical models are developed which are used to find the accurate results for observation of certain natural processes. Hence, for satisfaction of analytical issues, certain conditions are to be satisfied in order to get expected results. Every even on which theory of relativity is going to be applied must follow and regulate these conditions. This is the only way to match experience with conclusions. The complete theory of relativity is formed from two separate parts or collections of concepts and ideas. First one is general relativity and second one is special relativity. Both of these parts are connected with each other. Concepts from special theory of relativity can be applied on almost every physical phenomenon except gravitational force and related concepts. This loophole or limitation is solved by general relativity, which is consisting of law of gravitation. General theory of relativity also describes relation between gravitational forces and other physical force that tend to be similar to term gravity. No part of this theory is more important than other one. Even if general relativity is only about gravity, it is as important as special relativity, which consists of all other concepts rather than gravity. Both are equally important when applying theory of relativity practically. Fundamentals of theory of relativity. In the beginning, everyone has accepted relativity theory as a combination of more than one theory related to physics. Eventually, some limitation and exceptions were found for this statement. As mentioned, special relativity was invented or say presented in 1905 and final or say latest version of general relativity was disclosed in 1916. Both of these theories are applied practically in different areas of physical studies. For instance, concept of elementary particles is covered by special relativity. This part also covers studies related to interaction of elementary particles. On the other hand, general relativity covers cosmological realm, astrophysical realm, and astronomy only. Despite including very different concepts, general relativity and special relativity tend to be connected with each other through certain relations. Some concepts from one theory need to use base of concepts from other theory to be applied practically and vice versa. By the beginning of 1920, almost every community and personnels related to physics had accepted the concept of special relativity. In experiments in the fields such as atomic, nuclear and quantum mechanics, special relativity provides necessary concepts and ideas. Thus, it became popular among practitioners in these fields. Compared to this, general relativity appears to be less useful. Most of the concepts in general relativity were for astronomical scales. This caused its applicability to be limited for practical application and experiments. It was not able to contribute much in gravitation theory of Newtonian. It only made minor connections to predictions made in that theory. In addition, mathematical logics that appear in general relativity are very hard to understand and interpret. Applying them practically is even harder. In fact, only a limited number of people in that period were able to understand the concepts of general theory fully and interpret them to apply practically. General theory of relativity was highly discredited for this by Richard Feynman. Eventually, in 1960, general theory of relativity was accepted as central theory of physics and astronomy. Many new mathematical approaches were found that were completely applicable on concepts of general theory in order to find new stream of calculations which caused isolation of curious physical methods from complexity of mathematical approaches and calculations. Foundation of astronomical phenomena was a result to these subsequent events. Later on, astronomical phenomena contributed a lot in canalization of general theory of relativity. The astronomical phenomena consist of following concepts. Quasars that were disclosed to exist in 1963. Microwave background radiation discovered in 1965. Pulsars, black holes. First black hole was discovered in 1981. According to Newton's law, if two frames that are related with each other by certain reference and are moving relatively to each other with constant velocity, they will most likely to observe same physical behavior. There is no possible or practical way to figure out which frame is on the move and which is not. The term absolute frame or absolute velocity cannot be found here. According to Newton and his studies, if everything is relative, any frame resting or moving can be considered as a reference benchmark. Laws of electricity were discovered in early 19th century alongside with laws of mechanics. These laws describe that light or electricity is strongly related to phenomenon. Phenomenon is a kind of electromagnetic wave. Still, many practitioners and researchers believe that electromagnetic forces can be disabled using a proper subtle effect. They also believe that moment or steadiness of a frame could not affect on these subtle effects. Eventually, many researchers tried to practically using these effects to test those theories, which resulted as a big failure. Those effects did not work and could not identify the moving frame or system that is in motion. In 1905, principle of relativity was presented by Albert Einstein. He also considered his theory as a fundamental property that belongs to universe. In that period, detecting absolute motion at a constant and steady velocity was too hard. Many physical processes and concepts were applied to solve this theory, only to be proven fail. Some theorists believe that an error or missing link in laws of electricity or magnetism is causing such problem. This argument was proven wrong too, when everyone failed to find any loophole in any law or procedure, since changing these laws was more likely to ignore the theory of light and electromagnetic laws that are included in this theory. Einstein came up with a significant suggestion. According to him, Newton's law required modifications rather than laws of electricity or magnetism. While delivering such statement, he knowingly ignored the fact that Newton's laws has been already proven correct practically and described that absolute motion can be detected. These laws also suggested that time intervals that are measured in moving and resting frames cannot be considered as relative time in every case. The modification suggested by him was not applicable in every circumstance. His suggestion for modification was only considerable around velocity of light. The concept of velocity of light can be ignored in day-to-day phenomena easily. As researchers started to test these predictions practically, following facts became known. If velocity of light is approached by particles, they get even massive. This velocity is a superior upper limit of any particle that is impossible to pass. It finally became possible to demonstrate the relativity of time, thanks to the researchers that found that particles named muons possess a lifetime of about 2 microseconds. These particles are produced by cosmic rays in atmosphere. Researchers noticed that muons survive much longer than other particles and generally reach surface of Earth. The frame reference rate of Earth caused their lifetime to last a little bit longer. Special relativity. Special relativity is often referred as a theory of space-time, since this theory describes basic structure of space-time. As described, Einstein was the one to bring this broad theory with most usable and valuable concepts to light. Special relativity was introduced by him in 1905. He represented the concept of special relativity through his paper named On the Electrodynamics of Moving Bodies. Not only Einstein, but also many other scientists or physicists contributed their valuable work and research to build complete version of special relativity. Concepts of special relativity follow two rules commonly. These rules are extracted from classical mechanics. First, all the observers that are a part of uniform motion and are relative to each other possess the same laws of physics. This statement is also known as definition of principle of relativity. Second, all observers share very same vacuum speed of light. In spite of sharing same speed of light, they do not share similar relative motion or similar motion to the light source. This theory is based on practical experiments rather than classical mechanical procedures. For example, the second rule mentioned above describes the result of experiment held by Michelson and Morley. In addition, many surprising and as well counterintuitive consequences are caused by this special relativity. Some of them are described below. Relativity of simultaneity. If two unique observers are in same relative motion, two events may be simultaneous for one and not simultaneous for other observer. Time dilation. Observers' stationary clocks are much faster to tick than moving clocks. Relativistic mass. Physicists managed to develop this concept at its peak thanks to special relativity. Length contraction. If objects are measured from the direction that they are moving with their respective observer, they appear to be much shorter than they really are. Maximum speed is finite. It has been proven that no physical object is able enough to travel faster than the vacuum light. Vacuum light is proven to hold fastest speed in the universe than any other physical object, message, or even physical field. Speed of gravity. This concept helped to prove that gravity is not able to travel slower or faster than light in space. Gravity follows speed of light all the time while traveling through space. Galilean transformation, that is described in classical mechanics by Lorentz transformation, is replaced by a defining feature of special relativity. In the field of physics, special relativity is often referred as special theory of relativity, since it is a broad collection of various concepts, ideas, and principles. It is sometimes indicated as SR, special relativity, and STR, special theory of relativity. Generally, special relativity is widely accepted and tested theory. It describes the relationship, or say connection, between space and time. It was originally presented in 1905 to fill loopholes in research done by Newton, which lacked practical or experimental proof. Today, it is considered the most accurate model that is used to predict motion at any speed. However, Einstein never claimed theory of Newton to be useless. It can still be used with small velocities that are related to the speed of light. A main reason to use it is its simplicity and accuracy. The only special thing about this theory is that it can only be applied in special occasions where gravity turned the curvature of space-time into negligible. In 1915, Albert Einstein constructed a formula for general gravity in order to include the concept of gravity in the theory of relativity. Despite of some outdated descriptions, the theory of relativity is able enough to handle almost any reference from frames at accelerated state. A wide range of ideas, concepts, or say, combined consequences is included in special relativity. Concepts presented in special theory of relativity are verified both theoretically and practically. Following consequences are included in special theory of relativity: length contraction, time dilation, relativistic mass, mass-energy equivalence, a universal speed limit, and relativity and simultaneity. Many researchers use this theory as a replacement of conventional notion that is derived from absolute universal time. This derivation is done along with the spatial position and reference frame. The notion of time is very much dependent on these two aspects. This theory considers space-time interval rather than invariant time interval between two separate events. To predict equivalent mass and energy, special theory of relativity combines certain laws of physics and two postulates of special relativity. The formula for equivalent mass-energy formula is as following, in which c represents vacuum speed is the speed which an object holds or acquires in vacuum space. E equals mc square. If special theory of relativity is seen from a mathematical perspective, special relativity appears to be self-consistent. Additional resources of special relativity can be found in other theories also. Such theories include theories of modern physics, quantum theory, and string theory. Some resources can also be found in general theory of relativity, only in such cases where gravitational forces are negligible. General relativity. General theory of relativity was constructed by Albert Einstein during the time span of 1907 to 1915. General theory of relativity mainly covers concepts related to various gravitational forces, thus general relativity is often referred as theory of gravitation. Principal equivalence was used as a base in order to develop a complete theory of general relativity. According to this principle, accelerated motion and gravitational field are considered physically identical. Concepts of free fall and inertial motion are also considered. According to concept of free fall, when an object is free falling, it is in motion because it is a low object, rather considering gravitational force. Gravity is ignored in this concept because it is the case of classical mechanics, which have no relation with gravity itself or any other gravitational forces. Considering gravity is incompatible with special relativity and classical mechanics because, according to these concepts, objects cannot be accelerated by each other, but object in free fall can do it. To solve this confusion and complete the theory, Einstein suggested space-time being flat rather than curved. By the end of 1915, he successfully related space-time with the concept of mass, energy, and any momentum within the space-time. Some important foundations and consequences of general theory of relativity are listed below. General relativity presents concept of gravitational time dilation. According to this concept, clock runs slower when put in gravitational wells in deep. In general relativity, the way orbits act is not even expected in Newton's theory of gravity. This often happens with Mercury and binary pulsars. Gravitational field can affect light too. It has been observed that light rays bend their way when they pass through a gravitational force of any level. The bending cone very much depends on the energy level of gravitational field. According to a phenomenon named frame dragging, space-time that is around masses in rotation is dragged along with the frames. The most important argument made in general theory of relativity is that the universe is constantly expanding. It says that the far sides of universe are going away with faster than speed of light. These are some of the most important results extracted by general theory of relativity. In a technical perspective, general theory of relativity is theory of gravitation. This theory uses Einstein field equations as a defining feature. Metric tensors act as a solution for field equations provided by Einstein. They help in defining topology that space-time holds and describes how objects acquire motion initially. General relativity is often referred as GR, general relativity, or GTR, general theory of relativity. Albert Einstein has developed this theory in the year of 1915. This theory covers the concept of gravity in geometrical approach, thus it is often referred as a geometric theory of gravitation. General theory of gravitation covers the latest description of gravitation and related concepts that are suitable for various laws of modern physics. General relativity is said to be a simple generalization of special theory of relativity and Newton's law of universal gravitation. This combination provides unified description of gravity. According to this theory, gravity is a unified geometric property of space and time. General theory of relativity states that energy and momentum are directly in a relation with curvature of space-time. It also states that any present matter or radiation cannot affect relationship of these three aspects. This relation was specified by Albert Einstein in his field equations, which is a system of partially separated differential equations. Almost every prediction made in general theory of relativity has significant difference compared to predictions of classical physics. Some of the significant differences are listed below. Passage of time, geometry of space, the motion of object and bodies in free fall, speed and propagation of light, gravitational time dilation, gravitational leasing, gravitational redshift of light, and gravitational time delay. Every prediction made through general theory of relativity have been practically observed and confirmed to date. General theory of relativity is not just a theoretical matter. It is a simple collection of practical and experimental information and data. The most fundamental concept of general theory of relativity is that how this theory manages to reconcile with various laws of theory of quantum physics. By doing so, general relativity produces a complete and self-consistent theory of quantum gravity as well. Some important astrophysical implications are also included in Einstein's theory of relativity. For instance, Einstein presented the concept of black holes through his theories. As it is well known, black holes are in space where space and time are distorted. No physical particle or object, not even an object, can escape from its gravitational force. Black holes are automatically generated as a star enters its last stage of life. Einstein also said that black holes are the reason due to which certain kind astronomical are said to emit intense radiation in space. Ample evidence for such radiations was presented by Einstein. For instance, microquasars and galactic nuclei can only generate when stellar or even bigger black holes are present, since quasars and nuclei are generated from massive black holes. Concept of gravitational lensing is also a part of general theory of relativity. Bending of light due to gravitational forces gave birth to this concept. According to gravitational lensing, multiple images of the same astronomical objects to almost same distance are visible in the sky. Theory of general relativity also suggests existence of gravitational waves. These waves have been observed directly by an institution named Physical Collaboration LIGO. Experimental evidence of relativity theory. In this chapter, tests and experiments that have been conducted on theory of relativity are covered, along with their outcome and influence they made on the development and progress in the field of relativity and related concepts. These experiments and tests are divided into two parts, since the theory of relativity is also divided into two main parts, named theory of special relativity and theory of general relativity. Special relativity. Any scientific theories tend to make predictions which are then tested in practical experiments to figure out if they provide expected outcome or not. It is same with the theory of relativity too. In special relativity, these aspects include relativity principle, constancy and speed of light, and time dilation. Einstein established this theory in the year of 1905. Since then, prediction made by him has been proven through multiple tests and experiments. There were also some negative outcomes. 3 tests were made between the time span of 1881 to 1938. These tests or experiments came up with critical outcome for validation of special theory of relativity. Those experiments are listed below. Michelson-Morley experiment, Kennedy-Thorndike experiment, Ives-Stilwell experiment. Here is a broad discussion about these experiments. Michelson-Morley experiment. The main goal of this experiment was to detect ether wind as a second-order effect. Ether wind is motion of ether related with Earth. To accomplish this goal, an instrument called Michelson interferometer was developed by Michelson. As the name implies, the instrument was given name after its inventor. Accurate results were expected, but he got null results continuously in first two experiments that were conducted in 1881 and 1887. However, results were accepted by many scientific communities despite them being a big failure to detect ether wind. The interpretation of null result turns out to be that round-trip time follows isotropic pattern for time. Yet this theory was not enough to prove predictions of special relativity validate. These experiments showed that light hold an isotropic velocity. However, it said nothing about velocity of magnitude changing for every inertial frame. Kennedy-Thorndike experiment. For task left incomplete by above said research, this experiment was formed. Main goal of this research was to measure changing magnitude velocity for each inertial frame. First experiment in this research was conducted in 1932. Very similar to previous research, the obtained result was turned out to be null. As a conclusion, they represented that there cannot be any effect until the value of velocity is double than the orientation of orbit. Through their results, it was proved that round-trip time does not vary according to light in each inertial frame. Ives-Stilwell experiment. This project was carried out in 1938 by Herbert Ives and G.R. Stilwell. They also reconducted same project in 1941 with improved level of accuracy. The main goal of this experiment was to test transverse Doppler effect. This effect had been predicted by Einstein in 1905 in the broad Theory of Relativity. Comparing the observation of Doppler shifts with actual classical theory was the strategy in this experiment. Through this comparison, a Lorentz factor correction was observed. Based on that, they came up with the conclusion that moving atomic clock holds frequency that can be altered according to special relativity. Maxwell's equations. Light is described as a wave according to foundation of classical electromagnetism. This concept also describes that light holds velocity as a characteristics and moves along with it. As per modern view, light does not require any medium to transmit from one place to another. Maxwell argued this statement. According to him, light waves also transmit in a certain medium just as sound transmits in air and ripples transmit in surface of a pond. The hypothetical medium in which light transmits is called to be luminiferous ether. Earth moves on this same surface. Tests of general relativity. Many experiments have been conducted to confirm the validation of theory of general relativity. Most of them successfully validated it. Principle of equivalence and frame dragging has also been validated successfully through practical experiments. Some others are periphelion precession of Mercury orbit, deflection of light by the Sun, gravitational redshift of light, equivalence principle, and frame dragging. Applications of theory of relativity. Theory of relativity is currently being used in many modern electromagnetic devices that are being used by us in our daily routine. Global Positioning System, GPS, is a great example of such device. GPS. GPS system include three main components or parts: control component, space component, user component. Space component includes satellites that are situated in certain orbits. Control components contain a station to which all the data of location from space component is sent. Many concepts from theory of relativity are used while developing a GPS device. Various relativistic effects take place during a GPS is functioning. All of the GPS components belong to different reference frames, thus every relativistic effect must be accounted properly in order to get expected output from a GPS device. The GPS clock requires a regular synchronization. The gravitational field of Earth also needs to be accounted. Various gravitational effects take place during the functionality of a GPS device. For the precision maintained by GPS, the credit must be given to theory of relativity for providing such useful concepts. Other uses. Despite of this criticism, the results extracted by analyzing the relativity theory are excessively important for practical engineering. Practical engineering has concerns about theory of relativity in following concepts: GPS, Global Positioning System; GLONASS; Galileo, forthcoming one; concept of high precision dissemination of time. Following are some concepts in which theory of relativity has contributed a lot. They cannot be referred as application but have provided an important breakthrough in modern physics and other scientific researches. If two unique observers are in same relative motion, two events may be simultaneous for one and not simultaneous for other observer. Observers' stationary clocks are much faster to tick than moving clocks. Physicists managed to develop this concept at its peak thanks to special relativity. If objects are measured from the direction that they are moving with their respective observer, they appear to be much shorter than they really are. It has been proven that no physical object is able enough to travel faster than the vacuum light. Vacuum light is proven to hold fastest speed in the universe than any other physical object, message, or even physical field. This concept helped to prove that gravity is not able to travel slower or faster than light in space. Gravity follows speed of light all the time while traveling through space. Galilean transformation, that is described in classical mechanics by Lorentz transformation, is replaced by a defining feature of special relativity. Theory of relativity has contributed in following researches: quasars that were disclosed to exist in 1963. Microwave background radiation discovered in 1965. Pulsars. Black holes. First black hole was discovered in 1981. Following are some consequences that became possible only due to concepts of theory of relativity. Principle of relativity was presented by Albert Einstein. He also considered his theory as a fundamental property that belongs to universe. In that period, detecting absolute motion at a constant and steady velocity was too hard. Many physical processes and concepts were applied to solve this theory, only to be proven fail. Some theorists believe that an error or missing link in laws of electricity or magnetism is causing such problem. This argument was proven wrong too, when everyone failed to find any loophole in any law or procedure, since changing these laws was more likely to ignore the theory of light and electromagnetic laws that are included in this theory. Einstein came up with a significant suggestion. According to him, Newton's law required modifications rather than laws of electricity or magnetism. While delivering such statement, he knowingly ignored the fact that Newton's laws has been already proven correct practically and described that absolute motion can be detected. These laws also suggested that time intervals that are measured in moving and resting frames cannot be considered as relative time in every case. The modification suggested by him was not applicable in every circumstance. His suggestion for modification was only considerable around velocity of light. The concept of velocity of light can be ignored in day-to-day phenomena easily. Theory of relativity is the most famous and latest theory in the field of astrophysics. Most common and general concepts of theory of relativity are discussed. These concepts would surely help a beginner to get a breakthrough in this broad theory and eventually progress through every individual concept. This would be the best way to cover up this theory of gigantic size. Theory of relativity not only helps researchers in physics, but also in cosmology and astrophysics. This broad theory became concern for cosmology since the basic concepts as black holes are explained by theory of relativity. Many concepts that are a part of astrophysics use many concepts and ideas of theory of relativity as a base for further researches and explanations. Being a solid combination of multiple theories, theory of relativity becomes a thing of concern for practitioners of physics, astrology, cosmology, and astrophysics as well. Main concepts of theory of relativity are covered. Both parts of this theory, which are general relativity and special relativity, are discussed broadly. It will provide a breakthrough in the broad theory of relativity that will help beginners to cover broad concepts easily. It finally became possible to demonstrate the relativity of time thanks to the researchers that found that particles named muons possess a lifetime of about 2 microseconds. These particles are produced by cosmic rays in the atmosphere. Researchers noticed that muons survive much longer than other particles and generally reached surface of Earth. The frame reference rate of Earth caused their lifetime to last a little bit longer.